Hello, this is Dr. David A. Gaitros, Department of Computer Science at Florida State University, and I'd like to welcome you to my undergraduate lecture series on selected topics in computer science. You can find these videos and others at my YouTube channel at the URL listed below, or you can simply go to YouTube and search using Gaitros and FSU as keywords. Now on to the lecture. This is our lecture on computer organization, introduction part 3, and we're going over computer measurements. Original slides by Dr. Dave Wally, modified by Dr. Dave Gaitros. There are several factors that can affect the performance of a computer system, and these factors include the architecture, the underlying hardware implementation, the compiler that's used on the language or for that particular architecture, and the operating systems. To make definite measurements regarding the performance of any of these factors, one needs to hold all the other factors constants when taking the measure. So if you're going to measure the performance of the operating systems, then the architecture, the hardware implementation, and the compiler used needs to be remain constant so they can be compared equally. Okay. We often hear about latency and bandwidth, and here are the definitions. Latency is the response time, which is the time between an event is requested to when it's completed. Bandwidth is throughput, which is the total amount of work accomplished in a given period. Depending upon the application and users, sometimes one is more important than the other. Latency is more important on interactive systems, where an individual user is making a request, and bandwidth is more important for batch systems such as payroll. Sometimes both are important, such as an online flight reservation system, which has many interactive user requests. It makes sense that performance has an inverse relationship to execution time, since the smaller the time period, the greater the performance. So when one compares the performance of two machines, one should really compare the execution time. If machine X has greater performance than machine Y on a specific task, then the execution time for Y will be greater than the execution time for X. So here we have a problem. Okay. So let's say that we have a machine X takes 20 seconds to perform a task, the same task as machine Y, which takes 2 minutes to perform the same task. Then X is how many times faster than machine Y? Well, we have to normalize the comparisons here. First of all, X, we're talking about 20 seconds. Y, we say, is 2 minutes, which is really 120 seconds. So how many times faster? Well, it's 6 times faster, since it's 6 times less than machine Y. 6 times 20 is 120. Now we're talking about measurements of clock speed. On the slide here you see we have clock periods and clock rates. Okay. Clock periods are measured as milliseconds 2 to the minus 3. Microseconds is 10 to the minus 6th. Nanoseconds 10 to the minus 9, so on and so forth. Clock rates is the inverse of that. It's kilohertz is 10 to the 3rd. Megahertz is 10 to the 6th. Gigahertz 10 to the 9th, so on and so forth. So it's an inverse relationship. So when we want to convert one to the other, we have to inverse them. Also keep in mind too that whenever we do the conversions, we like to make whole numbers. For instance, I never reference something in terms of a half a gigahertz or anything like that. Okay, it's always 500 megahertz. Well, let's look at an example. If the clock period for a computer is 2 nanoseconds, and we'll look up there and we see it's 10 to the minus 9, then what is its clock rate? All right. Well, then let's go look at that. Okay. So we have 2 nanoseconds is 2 to the minus 9. Okay. We translate that is to 1 over 2 times to the 9th. Okay. And then to make it into a whole numbers, we borrow 3 from the 10 to the minus 9, made it 10 to the 6th. And of course what you do to the bottom, you have to do the top. I'm going to add 3 zeros up there too. So I take the 2 and I divide it into the 1000. What do I come up with? I come up with 500 over 1 times 10 to the 6th. And when we do the inverse of that, in other words, we bring the 1 to the 10 up, what we see is we have 500 times 10 to the 6th, or 500 megahertz. All right, and that's our answer for that question. Okay. Measuring of data size, and this is a term you're not going to see too often. We use specific terms to measure the amount of data. A bit stands for binary digit, B, and then the IT on the end of it. Nibble stands for 4 bits. Most people don't use that term anymore. In fact, I've never used it. I've been in the business for a long time. A byte is 8 bits. We use that quite a bit. A word today is typically 4 bytes or 32 bits, but the word size is really dependent upon the size of the architecture itself. And some machines are 32-bit word sizes, some are 64-bit word sizes. Most people refer to a kibibyte as 2 to the 10th bytes, but let me make a note about that. You're going to see kibibyte and kilobytes here. I've looked this up, and kibibyte, MIPS, gigabyte, tebibyte, and pebibyte all refer to the formal definition of 2 raised to a power. The kilobyte, kilo meaning 1,000, usually references 1,000 bytes, although some people actually do use 1,024 as kilobytes. Same with megabytes and gigabytes and terabytes. In this class, we'll try to be very formal about this. I'd like you to use the real numbers. In other words, I say kibibyte or kilobyte, I'd like you to reference as 1,024. Okay. Can CPU time be affected by other events? Yes, and since they may displace information from the cache or main memory, or may cause changes in the state in other architecture features, pipelining or things like that, CPI cannot really be looked at in a manual and get a reliable figure, since it depends on so many factors. So CPU time really needs to be measured in some way, and note that the CPU time can actually vary somewhat on executions. So suppose 2 implementations of the same computer here. We have up here the first equation just shows that the CPU is the product of the number of clock cycles spent during the execution and the time required for each cycle. And note that the clock rate is the inverse of the clock cycle time. The CPI is simply the total clock cycles for a task divided by the instruction count. Okay. The third equation shows the 3 factors of CPU time, which are the instruction count, CPI, and the clock periods. So here we have it. A CPU time, suppose 2 implementations of the same instruction set architecture are executing the same program. Computer A has a clock cycle time of 250 picoseconds and a CPI of 2. Computer B has a clock cycle time of 500 picoseconds and a CPI of 1.2. Which computer is faster and by how much? Okay. Well, if you plug those into the equations, and I encourage you to do it, what we see is that A is 1.2 times faster, which is 600 picoseconds over 500 picoseconds faster. Okay. As mentioned before, CPU can't be looked up in a manual. Pipelines can be flushed, branch information can be replaced, page translations can be evicted. So CPU time really not a very good measure. It depends upon the execution. Okay. Here we have Amdahl's law. It states that the performance improvements to be gained from using some faster mode of execution is limited by the fraction of the time the faster mode can be used. Now this just makes sense if you look at it. It depends upon 2 factors: the fraction of the time the enhance can be exploited and the improvement gained from it. So here we have a problem, and we see the Amdahl's law right here. And what you can do is you can plug the items into the equation. The speed of a CPU is improved by a factor of 5, and the CPU requires 40% of the machine execution time. Then what is the overall speed up? Okay, well, remember that you can only apply that factor of 5 to the 40% of the time. The other 60% is unaffected. Now, I'm not going to do the equation for you. I encourage you to do it yourself. But what you're going to come up with is, when you plug everything in, you're going to come up with 1 over 0.68, which means that if you take 0.68 and divide it into 1, that it's a speed of 1.47 times. Okay. Other measurements, here's some other popular measurements of performance. MIPS stands for millions of instructions per second. One can calculate MIPS by dividing the instruction count by the execution time in second times 1 million. So if the execution time was 1 second, then the MIPS would be instruction count would be divided by 1 million. If the execution time was 10 seconds, then we have to divide 10 as the instruction count, as how many instructions for the entire execution time. MFLOPS or megastop stand for millions of floating point instructions per second. Sometimes people who work in scientific applications realize that floating point operations is a limiting factor, so they're more concerned about that. There are several problems with using MIPS and megaflops. First, the power of an instruction set can vary between machines. Second, MIPS and megaflop ratings will vary between applications on the same machine. And finally, there are a number of other factors affecting execution time besides the number of instructions executed. For instance, a more powerful instruction set does more with fewer instructions and could have lower MIPS rating and still have a faster execution time. The issue regarding power has recently become important, so I'm going to spend a little bit of time on it. There are 3 reasons why designers are concerned about energy efficiency. There are now many processors on mobile systems, and these systems run on batteries. Many of you have to recharge your smartphones every day, or sometimes a couple times a day. Even for general purpose processors that run on constant power by plugging them into a wall socket, there's a need to be efficient. You've reached physical limitations that prevents clock rates from rising on processors, and they get hot or will fail. And one can see from the graph that the clock rate shown in megahertz rose for many years and has leveled off recently due to these physical limitations. And if we can be more efficient, we might be able to use higher clock rates. And the graph shows that power in watts has decreased while we've maintained the clock rate, since with new generations the voltage has decreased. Finally, the energy cost for computing has been increasing. Both computing needs to have increased as well as the cost of electricity. Probably most of you have seen this figure before, or at least something like it. It shows that if watts over a square centimeter kept increasing, then we could not afford to keep scaling the clock rate higher due to thermal constraints. Okay, as shown in the previous slide, this prediction was correct. The power has now gone down since we have a lower voltage with each new generation of processor, which is also why the power increased at a much slower rate than the clock rate. IT energy uses have estimated to be 2% of the worldwide carbon output and is expected to grow by 4% by 2020. We're only about 2 years away from that. And this is mainly due to the increased usage of computing by social society, from which a large part of these data centers. People have estimated servers alone require the equivalent of 6 million SUVs in the amount of carbon they produce. And from a business standpoint, it's important as many companies are reaching the point that their annual expenditures on power and cooling for IT equipment will be as much as their actual IT purchases themselves. This graph shows the energy that is used depends on the type of computer, and the pie chart shows the breakdown of energy usage in a Google data center. The data is from about 2009, which is quite old. We'll have to update that, but again, it shows a very, very good comparison. Power consumption on laptops, again, here you can see a laptop's power usage when it is idle on the left and performing a CPU test at the right. So even when it's idle, it still uses about half the number of watts. Embedded processing energy breakdown. This pie chart shows the breakdown of energy usage within a processor. The biggest portion is supplying data, and the clock and control logic require more energy than performing arithmetic operations. Here it shows that most of the energy for supplying instruction comes from the cache array that holds the instructions. And you'll learn more about this later on in other courses. Here is not the data array within the cache that's the biggest portion, but instead it's accessing the register file since it occurs so more often. But the amount for the entire data cache is half the total. Power is an instantaneous measure of the electricity used, and energy is the power used over a period of time. Okay. Dynamic power comes from switching transistors, and this is the formula we have for that. the power 1/2 times the capacitance load times the voltage squared times the frequency switch. Static power mainly comes from leakage, which is proportional to the number of devices being powered. Obviously, the more devices, the more the leakage. There are techniques to improve energy efficiency. You can turn off the clock for inactive modules, do nothing effectively. Use a lower clock frequency called frequency scaling, which can often allow lower voltages as well. Use a lower power mode for memory and storage when not being accessed, and completely turn on power to subsets of chips when not used. There's some fallacies and pitfalls in here. A commonly held misbelief: computers at a low utilization use little power. No, they still use power. So when they're plugged in, they're still drawing electricity. Designing for performance and designing for energy are unrelated. That is not true. They are very related goals. A pitfall, an easily made mistake: expecting the improvement of one aspect of a computer to increase overall performance by an amount proportional to the size of the improvement. That's not correct at all. You can increase the performance of a CPU and not affect the performance of the computer at all. And finally, using a subset of the performance equation as a performance metric. Again, you have to be holistic in your approach to this. Well, that concludes our introduction to the course. We're going to go on to the next portion of the class. Please play these over as many times as you need to. Enjoy doing them. Looking forward to the next one.